Microwave antennas, lens antennas, part 1, series on antennas and wave propagation, lecture number 5.14. Lens antennas belong to the category of aperture antennas. They are widely used in the design of microwave communication systems like radars. Their functioning is very much similar to the functioning of lenses in optics. This is first part of the session on lens antennas. In this session, lens antennas are introduced along with the types, categories that exist in them. The functioning of lens antennas is also explained along with their structural features, different modes of operation, various matching techniques adopted, zoning or stepping that is implemented over the surfaces of lenses. All these aspects are described and discussed in this session. Let us begin the session. As already mentioned, lenses belong to the category of aperture type of antennas. These are widely used at microwave frequencies in the design of radar communication systems. These are well known as collimators. What are collimators? Collimators are devices which convert diverging waves into non-diverging waves, thereby enhancing the directivity. Lenses are well-known collimators. When they are used as collimators, they work in combination with horn antennas. Horn antennas emit radiation which is diverging, and hence the gain or directivity associated with it is small. When a lens is placed in front of the horn, it converts the diverging emission of horn antenna into a non-diverging one, thereby enhancing the directivity. This is one application of lens antennas. Major application or widely used application. In this application, notice lens is being used as a part of antenna system. In fact, it is a secondary antenna. Primary antenna is usually horn antenna. Another application is also there for lenses. In this application, lens acts as an individual antenna. So lenses are also used as individual antennas at millimetric and submillimetric wavelength regions. These two regions fall in microwave band of frequencies. At these frequencies, they are preferred to dish antennas because of their superiority in terms of weight and performance. So lenses can be used or being used as individual antennas. They are also used in combination with horn antennas. Different types are there in lens antennas. They are mentioned in this slide. Lens antennas, as already mentioned, they are widely used as collimators, enhancing the directivity of a primary antenna, usually horn antenna. Two types are there. dielectric lenses, metal plate lenses in lens antennas. Dielectric lenses use dielectric materials for their construction, whereas the metal plate lenses use conductor plates for their construction. In dielectric lenses, again two types are there: natural dielectric lenses, artificial dielectric lenses. First type of lenses use natural dielectric materials, whereas second type of lenses use artificial dielectric materials. In metal plate lenses, also there exists two varieties: E-plane metal plate lenses, H-plane metal plate lenses. E-plane metal plate lenses are usually indicated as EPMP lenses in short form. Similarly, H-plane metal plate lenses are indicated as HPMP lenses in short form. As already mentioned, these lenses, metal plate lenses, use conductor plates. In EPMP lenses, the plates, metal plates, are parallel to a plane which contains E vector of the wave over which they work. In HPMP lenses, the metal plates are parallel to a plane which contains H vector, magnetic vector of the wave over which they act. There is another classification. All the lenses can be put in one of the two categories: delay type, fast type. Dielectric lenses and H-plane metal plate lenses, they belong to the category of delay type lenses, whereas E-plane metal plate lenses belong to the category of fast type lenses. What is the difference between delay type and fast type? In delay type, the lens medium provides delay to the wave motion. It slows down the wave travel. Whereas in case of fast lenses, the lens medium speeds up the wave. It makes the wave travel faster when the wave is passing through the lens. As wave is retarded, wave is slowed down, wave is delayed by the lens medium, those lenses are called delay type lenses, first type lenses. In second type lenses, fast type, wave is speeded up, hence they are called fast type lenses. In moving further, it requires to be mentioned here that delay lenses are also called slow lenses. Now we move to study the properties of lenses, slow lenses and fast lenses. In one column, properties of slow lenses are given. In the last column, properties of fast lenses are provided. Velocity in lens medium is less in slow lenses. It is more in fast lenses. Less in slow lenses means velocity of the wave in the lens medium is less when compared to velocity of the wave outside the lens medium. Same is the meaning of more velocity in case of fast lenses. Path length increases in slow lenses. It decreases in fast lenses. Index of refraction. It is more than 1 in slow lenses, nearly equal to 1.55. In case of fast lenses, it is less than 1, nearly equal to 0.55. Type or shape of faces. Shape. It is a plano-convex. In case of slow lenses, it is a plano-concave in case of fast lenses. Notice lenses antennas, they have one face always a plane, only one face is curved. It is for the purpose of reduced bulkiness, thickness. Shape of curved face is hyperboloidal in case of slow lenses. It is ellipsoidal in case of fast lenses. The mathematical relation that describes face shape is R equal to n minus 1 L by n cos theta minus 1 in case of slow lenses. This expression describes hyperboloidal surface. The symbols or letters in this expression carry their usual meaning. In case of fast lenses, the shape of curved face is ellipsoidal. The expression that describes this shape is R equal to 1 minus n L by 1 minus n cos theta. Dispersion characteristic. Slow lenses are non-dispersive, whereas fast lenses are dispersive, highly dispersive. What is dispersion? If the medium behaves differently for different frequencies, then the medium is said to be dispersive. Dispersion is usually a serious problem, serious inconvenience. Bandwidth. For slow lenses, it is an octave or more. For fast lenses, it is 2 to 10%. Examples for slow lenses are dielectric lenses and HPMP lenses. For fast lenses, examples are EPMP lenses. Now we consider the action of lens antennas while they convert diverging waves into non-diverging waves. In A is shown action of a delay lens or slow lens. In B is shown action of a fast lens. In A is shown a source, point source, emitting waves, electromagnetic waves. As it is spherical source, emitted waves exhibit spherical symmetry. As the source is a point source exhibiting spherical symmetry, the emitted waves possess spherical wavefronts. These wavefronts are diverging in nature, and hence the emitted wave is a diverging one. When a lens is placed, a delay lens is placed in the path of the waves, then the diverging wave fronts, after traveling through the lens, become non-diverging. We can notice before passing through the lens, the wave fronts are spherical. After passing through the lens, they are plane, non-diverging. How lens is able to convert spherical wavefronts into plane wavefronts? It is not difficult to understand the process. Any wavefront before passing through the lens can be divided into two parts. Let us consider this wavefront. A part of it, center part, it is ahead of other parts of the wavefront. When this wavefront is traveling through the lens, the advanced part of the wavefront, it is delayed by the lens medium. When the delay provided to this part of the wavefront is as required, then there is a chance for the lagging parts of the wavefront to catch up this advancing part of the wavefront, ultimately resulting in plane wavefront. Plane wavefront indicates a non-diverging wave with increased directivity. Now come to B. Here, a fast lens is shown in action. Here also, source is a point source exhibiting spherical wavefronts emitting a diverging wave. The diverging wave, after passing through the lens, it has become a plane wave, a non-diverging wave. How it happened? Here, what the lens medium does is it speeds up the lagging portions of the wavefront. Consider this particular wavefront. Again, it can be divided into two parts. One part is leading, this part is leading, outer parts are lagging. The lens speeds up the lagging parts. It provides advancement to the lagging parts of the wavefront. This makes the lagging parts of the wavefront catching up the leading part of the wavefront after passing through the lens medium. Outside the lens medium, after passing through the lens medium, the wavefronts are plane non-diverging. So in A, where the lens is a delay lens, leading portions of the wavefronts are delayed or retarded, making the diverging wavefronts into non-diverging wavefronts. Whereas in B, the lagging parts of the wavefronts are speeded up so that diverging wavefronts become non-diverging wavefronts, enhancing the gain. In both A and B cases, ultimate result is gain enhancement, directivity enhancement. Now a few points regarding performance of the lenses. Lens antennas. Lenses are aperture type antennas. Effective aperture can be determined from physical aperture, assuming an aperture efficiency of 0.6. Effective aperture is equal to 0.6 times AP. This 0.6 is more or less some standard value. Directivity can be determined from its effective aperture using the standard formula. D is equal to 4 pi over lambda square multiplied by AE. AE stands for effective aperture. Effective aperture can be computed from physical aperture. From directivity, of course, beam area and beam width can be found using the formulas. Omega A, beam area is 4 pi over D steradians. Half power beam width is under square root gamma A radians. One more point also required to be mentioned here. Lens antennas provide unidirectional radiation pattern, like the pattern provided by dish antennas. Now, a few points regarding dielectric lenses. In the beginning, it has been told that lenses are two types, dielectric lenses and metal plate lenses. Now, the points which are given here pertain to dielectric lenses. Dielectric, dielectric lenses fall in the category of delay lenses. Delay lenses are also called slow lenses. These lenses are fabricated using dielectric materials like lucite or plexiglass, polystyrene, polyglass, Teflon. These are all dielectric materials. If the dielectric constant of the material is large, lens becomes thin, but it suffers with reflections from the lens surface and consequent inefficiency. If the lens is fabricated with the low dielectric constant material, reflections become inconsequential, but and efficiency gets improved, but the lens becomes bulky. So it is a serious issue. Bulkiness is a serious issue regarding lenses. When it is bulky, it becomes difficult for mounting and maintaining the lens antenna at a proper location. Thus, the dielectric constant should be neither too large nor too small. Compromise values of index of refraction are 1.5 to 1.6 for dielectric lenses. Now we discuss about modes of operation of lenses, dielectric lenses. Lenses can be operated in two different ways. With the curved face towards the source and with the plane face towards the source. Here is source. One can place the lens with its curved face towards the source like this. This is one possibility. Another possibility is also there with the plane face towards the source. Each one has its own advantages and disadvantages. Now we discuss about them in this slide. In the first method, lens is called single refracting surface lens. And in the second case, lens is called two refracting surfaces lens. Why it is a single refracting surface lens in the first case? Reason is this. Wave gets emitted by the source and it travels like this, like this, like this, like this towards the lens. It falls over the surface of the lens. Here it gets refracted. After refraction, it travels like this, like this, like this. And then it falls over the other face, plane face, normally. So there is no refraction at plane face. Refraction now is happening only at one face or surface here. No refraction here. That's why in the first method, lens is called single refracting surface. Refraction is happening at one surface. Hence, the lens in this situation is called single refracting surface lens. In the second case, what is happening is refraction happens when wave falls over the plane face. Not only that, refraction happens even at the other face, curved face too. Here also refraction happens. Okay, in the first case, at the rear face, which is plane, the rays are perpendicular and hence they pass through this surface without any refraction. The disadvantage with this type of lens operation is reflection from the non-refracting surface can converge at the focal point and give rise to a reflected wave in the feed line. In the second type of operation, the plane faces towards the source, and usually the lens is placed at the focus. Sorry, the source is placed at the focus. The wave gets refracted at both the faces of the lens. It has the advantages of wide angle scanning ability and not refocusing the surface reflections back into the feed line. Despite all its superior performance, it is not being used in microwave systems because of its greater design difficulty. So most of the times it is single refracting surface mode that is used in the design of lens antennas. A few points regarding matching. What is matching? When the index of refraction is large, lens becomes thinner, but mismatch between lens and free space is greater, resulting in greater reflections energy loss at the lens surface. To understand the matching, consider lens antenna like this. Here is the source. Source emits waves. The waves travel like this, like this, like this. This is one ray, another ray. After traveling, the wave falls over the surface of the lens medium. Until now, the wave is traveling in free space. Now it is falling over lens medium. Lens medium is different from free space. There exists impedance mismatch between these two media. Hence, the wave, when it falls over the surface of the lens, it sees an impedance difference, an impedance mismatch. This impedance mismatch leads to reflection. So, result is incident wave partly gets into the lens medium, partly it gets reflected into space. The part of the wave that gets reflected into space, it is an energy loss. It makes the system inefficient. Reflections happen not only here at the curved face, they happen even at the plane face too. After traveling through the lens medium, the wave comes out of the lens medium at the plane face. While moving out from the lens medium, the wave again sees impedance mismatch as the wave is moving from lens into free space. When wave sees impedance mismatch, again reflections happen. This reflected wave partly moves. Part of the reflected wave moves towards the source side. Again, it gets reflected towards the plane face side. Again, it gets reflected back towards the curved face. And during each reflection, a part of the incident wave escapes into space. Net result is there exists multiple reflections inside the lens medium. At each reflection, there is an escape of wave energy into free space. The energy that is escaped at the plane face, of course, it is a useful one, required one, as it becomes as it is part of non-diverging wave. Due to mismatch, a part of the incident field gets reflected from the front surface. In addition, there exists internal reflections from both the faces, leading to multiple reflections within the lens. These reflections can seriously degrade the performance of the lens antenna, and hence it is necessary to match the lens surface to the free space, preventing reflections at the surface. So reflections here also require to be arrested, eliminated, prevented, or reduced as much as possible. And this reduction is effected with the help of a technique called matching technique. Front surface can be matched by a quarter wave dielectric layer having an index of refraction NL equal to square root of n, where n is Ri of lens dielectric and thickness equal to 1/4 wavelength, that is lambda by NL. This quarter wave thick dielectric layer is actually equivalent to a quarter wave transformer. Rare surface can be matched in a similar manner with a dielectric layer whose index of refraction and thickness depends upon both the incident angle and polarization of the incident wave. Since the incident field usually possesses co and cross polarizations, a perfect match for both of them may not normally be achieved. Here we are using the terms copolarization and cross-polarization. What is copolarization? Wanted polarization is copolarization. Unwanted polarization is cross-polarization. Copolarization and cross-polarization. These are usually normal to each other. Next, we move to another area of discussion on lenses, dielectric lenses, zoning. What is zoning? What is the need of zoning? The dielectric lenses become excessively thick or bulky when the wavefront is strongly curved and or the frequency is low, less than 10 GHz. The thickness or bulkiness is a serious problem. To cure this problem, zoning is adopted. The process of zoning, it is also known as stepping, is undertaken to reduce this excessive thickness as well as the weight of the lens. In this process, a certain portion of the material is removed from the lens body. Notice this removal is not arbitrary. Some calculations are there. Zoning can be done on either face of the lens, but the lens zoned over curved face is mechanically strong, even though it is a little bit involved process when compared to zoning over the other face. Thus, this process makes the lens compact in size as well as light in weight. So weight gets reduced, lens becomes compact when zoning is done over the lens. Then what is zoning? Here is illustrated zoning. In A is shown zoning on a plane face, in B is shown zoning on convex face, curved face. One can notice the material is removed by cutting the body of the lens in steps. The step thickness is indicated by T. Here also step thickness is indicated by T. So several steps are there. Stepwise material removal is done in zoning technique. Zoning process is based on the fact that a phase change of integral number of 2 pi radians at the aperture has no impact on the aperture phase distribution. This is the underlying principle of zoning technique. The thickness T of the zone step is selected in such a way that electrical length of T in dielectric is an integral, normally one number of wavelengths longer than the electrical length T in air. That is n minus 1 T equal to k lambda, where k is usually 1. Now, a few points regarding Demerits of zoning. Zoning makes the lens frequency sensitive, thus converting a wideband dielectric lens into a narrowband one. In addition, it causes loss of energy, decreasing its gain. Zoning steps also produces aperture illumination defects like shadowing, which cause an increase in the side lobe level. Some of these problems, however, can be cured by undertaking the process on a plane face or non-refracting surface. Notice zoning on a plane face reduces the strength of the lens. It is possible to avoid energy loss or shadowing, provided the surface of the step in between the zones is perpendicular to the zoned surfaces. It has been found that the bandwidth of a lens having n number of wavelength steps is 25 by n%. With this, we come to an end to the first part of a session on lens antennas. In this session, the focus is mainly on introducing lens antennas, their structural features, types, modes, matching, and zoning technique. In the second part on lens antennas, the focus is on artificial dielectric lens antennas and metal plate lens antennas. Hope this session is useful to you. We meet again soon in a session on second part of lens antennas.